Hello and welcome to today's Deep Dive. I'm your host, and today we are going to be exploring a really fascinating phenomenon. Have you ever been learning something new, like, I don't know, a language or maybe playing an instrument, and you just hit that totally inevitable plateau?
Oh, yeah. Hi, everyone. I'm your expert for today. And yes, that plateau is just an incredibly frustrating human experience.
Right, because you're practicing the same chords, you're running like the same vocabulary drills, but you just aren't getting any better. You've totally hit a wall.
Exactly. You feel like you're putting in all the cognitive computing power, so to speak, but the output just kind of flatlines. I mean, the effort simply doesn't translate into progress anymore.
Well, it turns out that the world's smartest AI models hit this exact same wall.
They really do. It's a known issue.
Yeah, they get so good at answering questions that they literally go numb. They just stop learning entirely.
Right.
But a new breakthrough has actually found a way to fix this.
Yeah.
This is wild. And not by feeding the AI into information, but by kind of forcing it to listen to its own moments of hesitation.
Yeah, the research driving this breakthrough is a really fascinating 2026 paper. It's titled EchoRL Reinforcement Learning via Rollout Echoing.
Which is a mouthful.
It is, yeah. But it was put together by a brilliant team from institutions like LMU Munich and Huawei, and they've essentially engineered a way for an AI to, break through its own developmental ceiling.
Okay, let's unpack this.
All right.
Because to figure out how they actually cured this AI plateau, we first need to look at why the models get stuck in the first place.
Exactly. We have to start at the root of the problem.
So that means diving into the post-training phase of massive language models, specifically a process called RLVR, which stands for Reinforcement Learning with Verifiable Rewards.
Right. And the industry standard framework for handling that RLVR process right now is called GRPO. That's Group Relative Policy Optimization.
Group Relative Policy Optimization.
Yeah, and the keyword to really focus on there is relative.
Okay, so let's break down that relative part for everyone listening. If I give the AI model a complex prompt, maybe like a really high-level math problem,
Sure, a tough math equation.
the model doesn't just spit out one single guess, right? It actually generates a whole group of different attempts, which are called rollouts.
That's spot on. It tries multiple paths.
Right. And then an automated system checks all of those final answers just to see if they are mathematically correct.
Yes. But here's where the relative part kicks in. Instead of just marking each individual answer right or wrong in a vacuum, GRPO grades the AI on a curve.
Oh, like in college.
Exactly like that. It calculates the average reward of that entire group of rollouts and then compares each individual attempt to that group average using variance or, standard deviation.
Got it. So it's basically looking for the standout student in the class. It wants to find the specific attempt that performs significantly better than the baseline average of all the other attempts.
Right, because it takes that standout difference and converts it into a learning signal. And in machine learning, we call that a gradient.
A gradient.
Yeah, and that gradient basically tells the model's optimizer, hey, whatever specific reasoning path you took on this highly successful attempt, do more of that next time.
But, and this is the core issue, as the model gets smarter through continuous training, we eventually hit that plateau we talked about.
We do. The paper actually calls this specific bottleneck advantage degeneration.
Yeah, advantage degeneration.
Right. The model gets so incredibly proficient at these problems that when you give it a prompt, it gets every single rollout in the group perfectly right.
Every single one.
Every single one. Every attempt gets a verifiable success score of 1.
Okay, I see where this is going. If every answer in the group is a perfect 1, then the group average is 1.
Exactly. And so the variance between those answers drops to exactly 0.
Wow. Because everyone got an A+, there is literally no standout student anymore. The variance is 0, which means the advantage score the system calculates just becomes 0.
And the gradient vanishes entirely.
The model just goes completely numb.
Right.
It's sort of like grading a classroom where every single student gets 100% on a test. As the teacher, you learn absolutely nothing about who is studying deeply, who discovered a brilliant new shortcut, and who is just, relying on rote memorization.
That's a perfect analogy. You just have a stack of perfect papers and 0 insight into how to improve tomorrow's lesson plan.
But hang on, let me play devil's advocate for a second.
Go for it.
If I'm training an AI and it starts getting every single answer perfectly right, shouldn't I be celebrating? Like, why not just toss out these easy questions where the variance is 0 and only feed it harder stuff? Rejection sampling seems like the obvious fix here, right?
That's what a lot of people think at first. But if we connect this to the bigger picture, Throwing out that data is actually a catastrophic waste of resources.
Really a catastrophic waste.
Oh, yeah. Think about the sheer scale of compute power required to generate these rollouts. We are talking about massive clusters of highly expensive GPUs.
Right, running super hot.
Exactly. Running hot, burning incredible amounts of electricity just to generate these perfect answers. Tossing them in the trash completely destroys your data efficiency.
Yeah, I mean, compute power is basically the ultimate bottleneck of the entire tech industry right now.
Yeah.
You can't just throw away perfectly good processing time just because the grading curve broke.
Exactly. You literally can't afford to. Now, another common workaround researchers try is leaning on external expert models.
Oh, like bringing in a bigger AI.
Yeah, exactly. They take a massive hyper-intelligent model, something like a DeepSeek R1, and they use it to generate golden trajectories.
Golden trajectories, okay.
Right. These are perfect step-by-step reasoning paths that the smaller model is supposed to just mimic.
Oh, so it's like hiring a wildly expensive private tutor to solve the homework on the whiteboard while the student just sits there, watches, and copies the notes.
Exactly. But that tutor is astronomically expensive to run at scale. And worse than that, it actually creates an infinite dependency loop. Well, a model can never fundamentally surpass its teacher if its entire concept of a good reasoning path is permanently restricted to what the teacher model outputs.
Right. It can only ever be as good as the model it's copying, never better.
Exactly.
So throwing away the data bankrupts us on compute, and relying on external teachers essentially traps the AI's potential. We have to somehow squeeze a learning signal out of a group of answers where the final destination, the final correct number is totally identical across the board.
We do. We have to look at the journey, not just the destination.
Okay, but standard GRPO is entirely blind to that journey, right? It only cares about the final verifiable reward.
Yes, exactly. Two identical correct answers can hide vastly different levels of intelligence, but the standard optimizer literally can't tell the difference.
And the researchers showcased this blindness with a really compelling case study in the paper, which I loved. They gave a language model a quartic polynomial math problem.
Right, a fairly complex math equation.
Yeah, and the model generated 4 different rollouts, which they called R1 through R4. And all 4 attempts absolutely nailed the final answer.
Right, and remember, under the standard system, because they all got it right, the advantage score normalizes to 0.
The optimizer goes completely silent.
Exactly. The model learns absolutely nothing from the exercise.
But if you dive into the actual reasoning steps inside those rollouts, it reveals a totally different story. Rollouts R1, R2, and R3 solve the polynomial using what we probably call brute force naive algebra.
Right, standard textbook methods.
Yeah, they differentiated the equation, did pages of super tedious algebraic expansion, carried all the variables the long way, and eventually just ground their way to the right number.
And I mean, that mechanical low-level reasoning works, but it is highly inefficient and really prone to cascading errors on harder problems.
Right. But then Rollout R4 took a completely different path. It deployed a novel algorithm.
This is the really exciting part.
It recognized a pattern and used a technique called the log derivative trick to completely bypass all that tedious algebra. It was this elegant algorithmic shortcut that saved massive amounts of processing effort.
And that brilliant mathematical insight is exactly what the standard system treats as background noise.
That's so frustrating.
It is, because R4 arrived at the same final number as the brute force attempts. The system just normalizes its advantage down to 0 and throws that beautiful, elegant shortcut right in the trash.
So how do we save R4? If all the final answers look identical to the grader, how do we build a radar to find that one moment of hidden algorithmic genius buried inside a pile of perfect scores?
Well, the researchers found that radar by measuring something called entropy.
Entropy. Okay, I've heard that term in physics, but how does it work here?
In the context of language models, entropy is basically a mathematical measure of predictive uncertainty.
Predictive uncertainty.
Right. So when a model is highly confident about the next token it needs to generate, say, when it is just reciting a well-known algebraic formula line by line, the entropy is very low.
Because it knows exactly what comes next.
Exactly. But when the model is synthesizing a novel reasoning path, standing at a critical decision point and weighing multiple complex options, its predictive uncertainty spikes. It exhibits high step-level entropy.
Oh, wow. Okay, here's where it gets really interesting, because you can compare this to watching a chess grandmaster play a match.
Oh, I like that comparison.
Yeah, like in the opening stages or when they are making an obvious recapture of a piece, they play incredibly fast. They don't even blink.
Right, low entropy.
Exactly. The path forward is certain, but then the board gets really complicated. The grandmaster pauses. They just sit there for 10 minutes staring at the pieces, hands hovering, deep in thought.
Yes.
That hesitation, that massive spike in uncertainty, that is exactly where the true genius is happening. That's where the game is won.
That is a brilliant way to look at it. The high entropy marks the hardest and most critical reasoning steps in the entire trajectory. And the research team actually proved this wasn't just a theoretical correlation, they proved it through an ablation study.
Okay, for the audience, an ablation study is basically where you selectively delete parts of a system just to see what causes the whole thing to break down.
Exactly. So they took these highly successful reasoning trajectories and started selectively deleting steps.
Sure.
When they deleted the lowest entropy steps, the fast, confident, rote memorization parts, the model's overall performance barely dropped at all.
Interesting.
Yeah, and randomly deleting steps had a similarly negligible effect. But when they started ablating those high entropy steps, the model's performance absolutely tanked.
The entire foundation of its reasoning just totally collapsed.
Right. It proved definitively that high step-level entropy is the perfect radar for finding usable learning signals. That peak moment of hesitation is the bottleneck. It is the exact moment of profound realization.
Okay, so we have our radar. We can look at a stack of 100% test scores, scan the reasoning paths, and pinpoint the exact spike in entropy where the AI paused, thought deeply, and did something truly clever.
Yes, exactly.
But if the standard GRPO system has already given up because the variance is 0, how do we isolate that specific spike on the graph without dragging all the boring low-entropy math along with it?
Well, this is the core of their solution. It's called EchoRL, which relies on a two-step process called rollout echoing.
Rollout echoing.
Right. The first step is echo clip mining.
Okay, mining.
The system scans the verified success rollouts and calculates the entropy at every single reasoning step. It is specifically looking for the absolute maximum step-level entropy.
The peak moment of thought.
Exactly. It then essentially takes out a pair of virtual scissors and snips out everything leading up to and including that specific high entropy step.
So it's basically isolating the struggle and the insight while leaving all the easy low entropy formatting that happens after the breakthrough completely behind.
You nailed it. That isolated snippet of reasoning is called the echo clip.
The echo clip.
Yeah. And then the second step is the EchoRL update. This is designed as a plug-and-play auxiliary module. You actually do not need to rewrite your primary training system at all.
Oh, that's convenient.
Very. You just take the echo clip and feed it back into the total loss function alongside the standard GRPO loss. You are literally echoing that moment of genius back to the model.
Wait, let me push back on this for a second.
Sure.
Because if my self-doubt was the only thing I focused on, I'd be totally paralyzed. If you feed an AI its own maximum confusion, its highest entropy data, doesn't it just break the model?
That's a fair point.
Like, won't forcing the system to hyper-fixate on its moments of maximum uncertainty cause the whole thing to second-guess itself into this massive overcorrection crash?
That is a very real danger, and it is exactly why the researchers implemented a critical safeguard. They needed a way to prevent the echo clip from drowning out the primary goal, which is, of course, arriving at the verifiable correct answer.
Right. So what's the safeguard?
They use a hyperparameter called lambda.
Lambda, the mathematical balancing weight.
Exactly. And they set the lambda value to exactly 0.001.
Wow. 0.001. That is an incredibly tiny fraction. How does a decimal point that small actually protect the entire system from crashing?
Well, think of the loss function as the model's steering wheel. The main objective, getting the correct mathematical answer, is the driver actively pulling the wheel.
Okay, I'm with you.
The lambda value is just a tiny 0.001 nudge on the power steering. So when the driver is actively steering, meaning when the primary gradient is strong, you don't even feel the nudge. The EchoRL update is just a tiny whisper in the background.
But when advantage degeneration hits, when the driver lets go of the wheel entirely because the variance has dropped to 0.
Yes, that tiny nudge is suddenly the only thing left. When the primary gradient vanishes, that whisper is the only voice left in the room. It sustains the training progress safely, keeping the learning gradient non-zero without ever overpowering the main objective.
That is so elegant. Snipping out echo clips and whispering them back through the steering wheel. It sounds incredible on paper. But when you apply this to actual massive language models out in the wild, Does it actually hold up?
Oh, the performance gains are tremendous. The researchers ran EchoRL across a battery of 10 demanding benchmarks using 5 different LLM backbones.
5 different ones.
Yeah, ranging from smaller 1.5 billion parameter setups all the way up to 8 billion parameter heavyweights like LAME 3.1.
Wow.
And they saw improvements of over 5% across the board, both on in-distribution math tasks and out-of-distribution general reasoning tasks.
5%. I mean, in the AI world, fighting for a 1% improvement is a bloodbath.
It really is.
EchoRL just gave these models a completely free 5% boost in general reasoning. That's like putting premium gas in your car and suddenly realizing you have a significantly bigger engine.
And it even scales to spatial reasoning, too. Like the Geometry 3K benchmark, which uses multimodal models that process images alongside text.
That's crazy.
But what's truly fascinating here is the correlation with model size. You might intuitively think a small patch like this would mostly benefit weaker, smaller models that need extra help, right?
Yeah, makes sense.
But the data shows the exact opposite. Larger models actually benefit far more from EchoRL.
Oh, wait. Because larger models are smarter, which means they hit the plateau faster.
Exactly. They start getting all the answers right much earlier in the training process.
Right.
And consequently, they spend a massive portion of their highly expensive training time with a zero gradient, literally learning absolutely nothing. EchoRL swoops in and continuously converts those discarded perfect rollouts into dense learning signals right when the massive model needs them most.
So for you listening, what does this all actually mean? Whether you're a developer training these systems or just someone who uses AI daily for work or research, this is monumental because of the cost analysis.
Yeah.
It's a true free lunch. The paper shows EchoRL introduces virtually zero additional latency or memory usage during training.
Zero. It is an incredible exercise in resource reuse. The standard GRPO process is already calculating log probabilities and rewards in order to function at all.
Right.
So EchoRL simply piggybacks on that existing math that's already sitting in the GPU's memory. Computing the step-level entropy is just a mathematical reduction over data that's already there.
It makes the AI smarter, faster, and significantly cheaper to train, all without requiring those expensive external teacher models.
Exactly.
And we know it's not just cheating the test, right? One of the best details in the paper is how they track the mean response length. The AI isn't just writing incredibly long, rambling answers to fake its way to a high score or artificially inflate its entropy.
No, not at all. The response lengths map perfectly with standard models. It is winning by utilizing better reasoning, not by just boosting its word count.
Which is so cool.
It is, and that points to a deeper training dynamic the researchers observed. Without EchoRL, standard models suffer from what is called entropy collapse.
Entropy collapse.
Yeah, the model converges on very narrow, safe, repetitive reasoning paths. It essentially gets lazy. It stops taking risks and stops exploring new ideas. EchoRL forces the model to maintain a healthy level of internal entropy, constantly incentivizing it to explore new, highly uncertain, and creative ways to solve problems.
That's amazing.
Yeah.
So we started this deep dive talking about the sheer frustration of hitting a plateau. We've seen how the world's most advanced AI models hit that exact same wall when they get too many right answers, when the variance drops to zero and the learning signal just completely vanishes, wasting massive amounts of compute power.
Right.
We explored how researchers tapped into entropy, which is essentially the mathematical signature of hesitation, to locate those hidden moments of algorithmic genius inside those perfect scores.
Yes.
And we unpacked how EchoRL takes virtual scissors, snips out those moments, and reflects them back, offering a massive, completely free boost in intelligence and creativity.
It really is a game changer. And I think this raises an important question, something really profound for you to think about as we wrap up today.
Oh, definitely.
EchoRL proves definitively that AI models have the capacity to mine their own hesitations to reach entirely new levels of genius. They don't need human oversight, and they don't need massive teacher models holding their hands anymore.
Yeah.
So if AI can now autonomously recognize its own moments of brilliance and reinforce those moments simply by measuring its own mathematical doubt, are we looking at the foundational architecture for AI systems that can infinitely self-improve, entirely in isolation?
Wow. That is a wild thought to leave on. Thank you so much for breaking this down with me today.
Anytime. It was a blast.
And thank you all for joining us on this deep dive. We'll catch you next time.